The Colmar Hsqc web server is our simplest and most straightforward tool for the automated query of a 2D NMR spectrum of a metabolomics sample against our Colmar metabolomics database. The web server will return a list of metabolites that are likely present in your sample. It allows the user to upload a carbon-13 proton Hsqc cross-peak list, which the user has compiled manually using their favorite software, and query it against the database for metabolite identification. You will get there in 3 simple steps: data upload, data referencing, and database query. The Hsqc cross-peak list is a text file which contains proton and carbon chemical shifts in columns separated by a space. We recommend that you reference your peak list with respect to DSS or TMS before upload. Alternatively, you can have your spectrum auto-referenced by the web server using one of the 5 common metabolites, such as alanine or glucose, that are present in your sample. Example Hsqc peak lists for valine and extract from Drosophila flies, both referenced and unreferenced, are available for upload so that you can familiarize yourself with the web server features before you upload your own data. I will demonstrate loading the data and referencing with the unreferenced Drosophila data. Starting in the Step 1 box, clicking here on the example data will load the Hsqc peak list. You can alternatively upload your data by copying and pasting your peak list or by uploading a text file. As an example, I will load the unreferenced Drosophila data. Next, click Plot Input Peaks. When scrolling down, you will see your peak list displayed as a 2D scatter plot with proton chemical shifts versus carbon chemical shifts as blue circles. This corresponds to a simplified mock representation of the original Hsqc spectrum from which the cross peaks were picked. Next, the data need to be properly referenced with respect to their chemical shifts. The peaks for 5 common metabolites are shown in a variety of colors. Of these 5, you should use the metabolites that are present in your sample for referencing. In this case, you can see my blue peaks overlaying well with 4 of the metabolites. I would use all but leucine, shown in pink. To remove, click leucine below the plot. Notice that upon unchecking, the metabolite is now grayed out in the list below the peak display. Or you can go to the Step 2 referencing box and uncheck leucine there. Click Calculate, and you will see the referencing values auto-calculated based on a pattern matching algorithm between your experimental peaks of the 4 compounds you have selected and the database peaks. These values correspond to the difference in chemical shift of your input peaks and the reference peaks in the database. To visualize the peak adjustments, you can look at the plot. An X marks the peaks that now match the target metabolites. Clicking Apply the Referencing will adjust your input peak list. Be aware, if your peak list is quite far off from our reference compounds, the auto-referencing may fail. This is apparent after clicking Calculate. If the referencing values it suggests read 100 for both the proton and carbon, then the peaks are too far off for auto-referencing and must be manually referenced before upload. Last is the database query and display to identify the metabolites that make up your peak list. Notice the user has 2 options, shown as different Step 3 boxes, which slightly alter how the database is queried. In both options, the user has the option to set chemical shift cutoffs, which sets the tolerance for how much the input peaks can vary from the database peaks, and return a match. The default setting is 0.03 ppm for proton and 0.3 ppm for carbon, but these can be edited for a more or less strict interpretation of the data depending on the application and your confidence in the accuracy of your peak list. In the first Step 3 box, the matching compounds are automatically filtered by uniqueness and matching ratio. This takes into account if compound peaks are overlapped with other compound peaks in the spectrum. The matching ratio gives the ratio of the number of peaks present for a compound in your peak list divided by the total number of peaks expected for a compound. The web server combines this information to assign peaks, which may match to multiple compounds, to the most probable compound only. Therefore, a peak assigned with high confidence to a compound will not be assigned again to a low confidence compound. In the second Step 3 box, the matching compounds are not automatically filtered by uniqueness, so this will return a less specific compound list. Instead, the user can manually set the peak matching ratio cutoff. The default is set to 0.6, meaning 60% of peaks expected for a compound must be present for a compound to be returned by the web server as a match. So if multiple compounds fit your chemical shift and matching ratio cutoffs, then they will be returned as possible matches even if these compounds share a peak. Try both options and decide which is better for your purpose. Go to Step 3 and add your name and affiliation. This information is only used internally for usage reporting and helps us to keep Colmar funded by the NIH. Manually modify any cutoff default values as you see fit and click Submit, and the database will be queried. Only compounds within the matching parameter cutoffs will be considered as a possible match. The cutoff values can be easily edited and the query repeated to monitor the effect on the returned metabolite list. A plot will appear that visualizes your results. Peaks that match multiple compounds are shown as a thick blue circle. Peaks matching single compounds are shown as a thin blue circle, and peaks matching no compounds are shown as a black cross. The black crosses represent cross peaks that may belong to unknown metabolites and can be pursued at a later stage using other methods. Below the plot, a list of the names of the matched compounds will appear. You can click any compound name to see the peaks highlighted on the plot. A table shows the metabolites matched and details such as deviation from the database peaks, matching ratio, and uniqueness, which can be used for deciding which metabolites are confident matches. Clicking Show Me will highlight the peaks belonging to that metabolite in a specific color. Each metabolite in the list can be highlighted, and to remove the highlights, simply click Clear All. Compound and peak information can be downloaded by clicking here on the tar files. As you can see, this web server produces fast and useful results for metabolite identification. When you begin a study with a new sample, this is often an excellent first step as it gives you a good overview of the number and identity of metabolites present in your sample. However, it requires the user to compile their own cross-peak list from the Hsqc spectrum. Also, remember that Hsqc peaks alone did not show whether they belong to the same or to different metabolites, which makes the query based on Hsqc data alone potentially ambiguous. Both of these drawbacks are addressed by our more sophisticated Colmar M web server, which is described in a separate video. Thank you for watching. When you publish results obtained from our web servers, please reference our corresponding papers shown here. This is important to keep the web server supported by OSU and the NIH. We welcome questions, comments, and suggestions from our users. We are also open to requests for collaboration, which can be directed to Dr. Raphael Bruschweiler. Thank you.